Hello, everyone. I'm Lijun Zhang from Nanjing University, China. I'm going to talk about our recent work on empirical risk minimization for stochastic convex optimization. This is journal with Tianbao and Rongjin. So this is the outline of my slides. First, let's see the introduction. So we consider the problem of stochastic optimization. I think we are all familiar with this formulation. We want to minimize the population function capital F, which is defined as an expectation of a random function, a small f over the distribution P. Here the distribution may be unknown to us. So in a very special case that the domain capital W and the function capital F are convex, we say that the problem is stochastic convex optimization. So for this problem, a very well-known special case is supervised learning. In supervised learning, we want to minimize this function. This here, the capital H is a hypothesis class. So xy is a label and the instance label pair. So L is the loss function, so which measures the prediction error. So in supervised learning, we want to minimize the expected loss. So this is just a special case of stochastic optimization. So to solve the problem, the most standard way is the sample average approximation, which is also referred to as empirical risk minimization in machine learning. So for stochastic optimization, we just sample n functions f1 to fn from the distribution. Then we define the average function as f hat. Then our problem becomes minimizing f hat over the same domain. For supervised learning, we will sum data. We will sum n data x1, y1 to xn, or yn from the distribution, and we minimize the average loss over those data. So they say the problem becomes the same. So another one for stochastic optimization is the stochastic approximation. So one of the most familiar methods is SGD. I think we're all familiar with this method. So in this paper, I will talk about the empirical risk minimization instead of SA. Okay. So to measure the performance of empirical risk minimization, we will introduce excess risk, which is defined as the difference between FW hat minus the minimal risk. Here W hat is our empirical minimizer. Here W star is the optimal solution. So this will measure the performance. ERM has been extensively studied in statistics and in machine learning. However, most of the previous work are restricted to supervised learning. I just randomly select some papers and books. You can see we can find many studies on this topic. However, the study of ERM for stochastic optimization are very limited. I can only find a few papers on this topic. So actually, those two settings are different. So the result in this setting cannot be extended to this setting. Okay. So let's see our contribution. First, we derive new risk bounds of ERM for stochastic convex optimization. The key point is that we will introduce the smoothness. We will derive this. First, we will derive this bound. Here, D is the dimensionality of the data of the domain, and N is the number sample. F star is the minimal risk. So in this case, we will have 1 over square root of n rate. Right? However, if F star, the minimal risk, is very small, we will get 1 over n rate without strong convexity. Okay. If we have both smoothness and strong convexity, the risk bound is improved to D over n plus kappa F star over n. Here, kappa is the condition number. So in this case, we will get 1 over n rate. We always have 1 over n rate. The most surprising result of this paper is that we derive faster rates of ERM for both stochastic convex optimization and for supervised learning, which shows that if the number of samples is large enough, for example, if it's lower bounded by kappa D, kappa is the condition number, D is the dimensionality, and with smoothness and strong convexity, for stochastic convex optimization, the risk bound can be improved to 1 over lambda n squared plus kappa F star over n. So if F star is small in this case, you will get 1 over n squared rate. Okay. Similarly, for supervised learning, which shows that if n is lower bounded by kappa squared, you also get the improved rate.
What is lambda?
Lambda is the strong convexity. Is lambda strong convex. Okay. Kappa is L over lambda. L is the smoothness. Lambda is strong convexity. Okay. So this result is the first result shows that the X risk bound can go beyond 1 over n. So in the previous study, even when F star is 0, the upper bound is still 1 over n. So this is the first time that it shows that the upper bound can go beyond 1 over n. Okay. Now let's see some related work. So as I said, the the existing study of EM are very plentiful. So here I just cite some papers that list some papers that are most related to our results. So we all know that in general, the exercise response can be bounded in terms of the complexity of the hypothesis class. So the most well-known one is the weight dimension, which is data independent. So in general, we get square root of weight dimension over n rate. So another one is the random number complexity, which is data dependent. With random number complexity, you can see that the response is on the order of 1 over square root n plus the random number complexity. In general, this quantity is also on the order of 1 over square root of n. So finally, we also get 1 over square root n rate. Right. Later, cerebral introduced smoothness in this setting. This shows that with smoothness, the response can be improved to square of random number complexity plus random number complexity times square root of f star. So then you can get this result if random marker is on the order of 1 over square root of n. Okay. So in this case, you get this rate. If f star is very small, the risk bound improved to 1 over n rate. Okay, this is the faster rate. If we also have strong convex, that is, if the population function is strong convex, we also have the 1 over n rate. The lambda is the parameter for strong convexity. Okay. So next, let's see the existing result of ERM for Stochastic optimization. In this setting, the results are very limited. In this work, Shalev-Schwartz shows that if the random function is Lipschitz continuous, we can get square root of d over n. D is the dimensionality, so that's rate. If the random function is strongly convex, we can improve it to 1 over lambda n rate. However, this result only holds in expectation. It's not a hyperability bound. All the other bounds are hyperability bounds. Okay. For exponential concave function, we also have 1 over n rate. It's also faster rate. Okay, next let's see our results. So first, our results for stochastic convex optimization. Before I show the result, I will first summarize the existing results in this picture. Okay, so the top arrow shows the response of ERM for stochastic optimization. Okay, with these two results here. This is Lipschitz strong convex. Okay. For supervised learning, the result is summarized in the bottom arrow. So Lipschitz strong convex. So from this picture, you can you can see that Lipschitz has been studied in both cases. Strong convexity also has been studied in both cases. So then it's natural to ask, can we use smoothness to improve the rate of stochastic optimization? So for this question, we give an affirmative answer, which shows that if we have smoothness, the risk is improved to d over n plus f star over n. So you can compare this result and see that the difference is that in stochastic optimization, we will have the dimensionality here. But here we don't have the dimensionality. It's 1 over n plus square root of f star over n. Okay. Now let's see the theorem. I first introduce some assumptions. So this is the assumption used in our theorem. First, assume that the domain is a convex subset of the d-dimensional space, and it is bounded. Then assume that the random function is non-negative, smooth, and convex. Assume that the population function is Lipschitz continuous. And finally, we'll assume that the stochastic gradient at the open solution, just at this one point, is bounded. It can be unbounded in other place. Okay. Then with hyperability, you can say that, so can prove that the risk bound is on the order of d over n plus square root of f star over n. As I said before, in this case, if f star is small, for example, if we choose this order, we get 1 over n rate. Okay. Now let's move to our next result. So from the picture, you can see that I already mentioned that for strong convex, although we have 1 over lambda n rate, but it only holds in expectation. But here, the 1 over lambda n rate here is holds with hyperability. So we may ask, can we derive hyperability bound for this strong convex case? We show that if we have both smoothness and strong convexity, we do have a hyperability bound. In this case, the bound is on the order of d over n plus kappa f star over n. Okay, let's see the details. Okay. This is the assumptions. Compared with the previous one, the only difference is that we assume the population function, the expected function, is lambda strongly convex. With this additional assumption, we can derive this response. Now we may want to compare our result with the result of Shelley-Schwartz. In his paper, he proved this bound. So first, there is a limitation of our result, is that we have linear dependence on the dimensionality D, right? So they don't have the dimensionality in their bound. So if D is very large, our bound is somehow worse than their result. However, if D is small, they are on the same order, because kappa is a condition number. It's on the order of 1 over lambda. You can think, we roughly can think in this way, right? However, we do have two advantages. First is that our bound is hyperbolic bound. The second is that for the surrounding convexity, we only assume the population function is surrounding convex. But in this paper, they assume each random function is surrounding convex. So our assumption on surrounding convexity is much weaker. So for example, for the square loss, for each individual random function, it can be surrounding convex. But the expectation could be convex if the covariance matrix is full rank, right? So our results have other advantages, but some limitation. Okay. Now let's move to the next result, which is the most surprising result in this paper, which shows that if the number of samples is lower bounded by kappa D, then the risk bound can be further improved. Okay, let's see the theorem. The assumption is the same as the previous one. The only difference is that if we have this condition, if the number of samples is lower bounded by kappa D times log n, the risk bound can be improved to 1 over lambda n squared plus kappa f star over n. So for this result, as I said, if f star is small, we actually get 1 over n squared rate. And this is the first time the risk bound is go beyond 1 over n. Okay, next I will give some two extensions. So this is, we have proved the results. For the last two results, I gave two extensions, which shows that the individual convexity on the random function can be relaxed. So if we, without the individual convexity, the risk bound will increase. So the first term will increase by kappa factor. The second term is on the same order. So if without individual convexity, we will pay the price of kappa. So if without individual convexity, to get this improved risk bound, we also need to increase the lower bound by a factor of kappa. So its kappa D now becomes kappa squared D. Okay, this is our two extensions. Now let's see the theorem. The theorem is this is the assumption. So first is the assumption. So here, the random function do not need to be convex. We remove the convexity of the random function. However, we do need to assume the empirical function f hat is convex. So in this case, this will increase by a factor of kappa, the first term. Okay, so they both have a kappa factor. To get the faster rates, the lower bound is increased by a factor of kappa. In the previous one, it is kappa D, now it's kappa squared D. Okay. Right. Now let's see our results for supervised learning. So this is what we get now. So we prove the faster rates for stochastic optimization. So we may ask, can we get a faster rate for supervised learning? The answer is yes. For supervised learning, we show that if the number of samples is lower bounded by kappa square, we also get a faster rate. So in this case, you can see that the lower bound of n don't depend on dimensionality. It is dimensionality independent, which means that this result can be applied to the case that the dimensionality is infinite. So for example, for learning with kernels, this result can also hold. So for supervised learning, if n is large enough, you also get a faster rate if f star is also small. Right. So this is okay. Let's see. So our setting. So for supervised learning, we consider the case that the prediction function here, the prediction function is the inner product is a linear form. It is w and x the inner product. The reason is that with this setting, we can take the derivative easily. Otherwise, it's difficult to take the derivative. Okay. With this setting, we can also add some regularizer, but we can also remove it. But we do support the regularizer case. So then the problem of EM in this case, we sample data and we regularize the empirical risk. Okay. Then we introduce FH to define as the expectation of the risk. Now let's see our theorem. This is our theorem. Theorem says that there are some common assumptions. That is, W is a convex set of the hyperspace and it's bounded. And so we assume that the loss function is smooth, non-negative, and the regulator is Lipschitz continuous. The population is surround convex, and f hat is convex, the empirical function convex. Then we show that with the kappa square lower bound of n, we get faster rates. Okay, so in this case, we also get, if h star is very small, we also get 1 over n square rate. Okay, now I will say something with our analysis. The analysis is very simple. So it's based on this inequality. It's very straightforward to get this inequality. It's based on convexity, you can get this inequality. The novelty comes from this last step. This is the equation, you see that. So we introduce the difference of the gradient, and we bound these two terms. So first we bound this term, the A. To bound this term, you can see that the because W hat depends on F hat, so we need to prove a uniform convergence of the difference of the gradient. It can be proved easily by using the Carving number, the concentration integrity of vectors, and the smoothness, property of smoothness and convexity. So if we compare our analysis with the previous one, so in a traditional analysis, they all bound the uniform convergence of functions. They bound the difference between f and f hat. Here we bound the difference between their gradients. That's the reason that's why we can get a faster rate. Okay. If you bound this term, no matter what the concentration increase that you use, you will get a 1 over n term, right? But if you bound the gradient, for example, you bound this term, you get a 1 over n rate. Then you can take a square, you get a 1 over n square. And this part, you take a square, then will cancel with surround convexity. So that's the reason. So we bound the uniform convergence of gradient so we can get the faster rates. This is the key idea. Okay. Then this term can be bound easily by vector concentration because W psi is independent from F hat. Okay. Okay, let's conclude our work. So we derive some faster rates and the new risk bound of ERM. So the ERM and open problem. First, this hyperbolic bound for surround convex case has a dependence on the dimension D. So we want to know is it possible to get dimensionality independent bound that holds with hyperability? Okay. The second is that we have several fast rates. They all have a lower bound on n, right, on number of samples. We believe the lower bound is necessary, but I don't know whether it's tight. So we also investigate this problem in the future. Okay, thank you.
Yes, we have time for questions while the next speaker sets up.
Can you explain again why you get better concentration for gradients and for function values?
Yeah, okay.
Please repeat the question.
Okay. So why we get a better concentration inequality if we bound the gradient, right? For this term, if you bound this term, you will get 1 over n rate, right? In some cases. So here, if you bound the gradient, you get 1 over n rate. Then you can take a square. So A times B is smaller than A square plus B square, right? So you take a square, you get 1 over n square. This part you get a square. The square will cancel with the surround convexity. So you will get faster rates.
Any other questions? Okay, one more? Yep.
Sorry, I will be quick. In the case where D is finite,
yeah.
kappa is also finite?
But
Kappa is always finite, right?
pi.
So, I mean, asking n to be lower bounded by kappa, then
Yeah.
kappa D, you just mean n is not constant?
It's constant.
The big O is already going to infinity, so I don't see the point. I don't see how can you get a faster rate in this case because the assumption is not anything else, right?
You mean the lower bound on n is not necessary?
Okay, maybe we can discuss after.
Okay.
Okay, so let's thank the speaker again.